configuration, consisted mainly in the outer shell of the spaceship's structures, sequencing their resistance and tolerance in various decay conditions.
The material map of a spaceship is constantly related with the active and passive artificial intelligence navigation system of a spaceship. The materials map of the spaceship, under the context of a specific structural design strategy, could represent it as the canvas fabric transformation system of the outer spaceship structure that is constantly adapting and providing two major functions for the artificial intelligence spaceship system: propulsion surfaces for navigation and environmental structural operations for crew safety and functionality. From materials perspectives, it is possible the artificial intelligence system of a spaceship to be stored and function under a selective mode as a separate independent entity and physical unit, outside the physical structural and navigational coordinate system of the spaceship. It is possible, for a given dimensional space-time, the propulsion and navigation artificial intelligence operations (PNAO) of a spaceship, to interact with another dimensional space-time (PNAO) that is in a parallel relativistic existence and in a much more extended coordinate system. The idea of a functional PNAO that is operated using specific isotopes, located in the form of a matter in special conditions, several times greater the age of the presented Planck timescale universe, is already a fact of reality. One possible material that could be selected to sustain PNAO interactions are some isotopes of tellurium, where their longevity could exceed several times the age of this current state of the universe. The isotope 128 of tellurium is the longest half-life among all radionuclides, which is approximately 160 trillion or 1012 times the age of the known universe. The PNAO can also proceed as a spaceship clocking metric mechanism, also a crucial coordinate navigation operation concept, for the case of the Alcubierre warp drive research. The propulsion surfaces of a spaceship can be operated by the executive configuration of the materials map of PNAO, in relation with a given space travel interaction conditions. It is also a much safer strategy, the distributed navigational guided functionality, to be proportionally distributed with the distant relativistic operation travel energy requirements chart modes, while the artificial intelligence mechanism can be applied to a multitude of space-related objects and distances trajectories and providing for the crew the right envelope of navigation decisions during their spaceship travel, maximizing the overall safety for the crew operations. All these interactions, to this extent, can provide reconfiguration stages before and during the propulsion surfaces operations, optimizing the overall relativistic path of the materials interactions. This is a crucial structural design functionality parameter for a spaceship structural designer, selecting what are the passive and what should be the active artificial intelligence characteristics of the embedded propulsion surfaces drivers. For example, fermionic and non-fermionic matter sometimes can operate as insulator for a given propulsion system interaction layer, other times as reactive surface shell with relativistic structural characteristics in the lattices. We have seen this with the element of palladium in a fusion reactor operation, with known decay and corrosion problems. In a closer conceptual detail mode, these spaceships' surfaces operations could sustain and shield configurable extreme materials interactions conditions, starting from the presence of Fermi temperatures, instant and scaled degenerated matter interactions, gluon plasma inner wall interactions with extreme magnetic fields. The development of such spaceships' surfaces primary will be linked with PNAO in order to respond to unprogrammed violent events that can occur during space travel, like supernova burst, extreme dense cosmic ray events or magnetar avoidance interactions, especially where simple opposite way out trajectories is not an option during ultra-relativistic speeds, conditions that could be formed between wrap mode conditions for example.
The concept of the propulsion surfaces for a spaceship can also provide crucial structural answers on demand concerning virtualization decision-making for alternative paths of navigation, related directly with actual representations of the spaceship's structural condition, probing rapid adaptations for the inner structural spaceship shell environment, where the sustainable crew protection and functionality is the ultimate operational goal.